This is Group 39, and this is our progress report on our quantitative risk assessment of deep water risers.
Hi, I'm Billy Compton, and I'm going to talk about the cost of SCRs. The cost of a pipe is going to be measured by weight. For a given pipe, outer diameter, pipe weight per unit length increases linearly with the wall thickness. It is estimated in dollars per ton. My two criteria are API RP 1111, which mandates the burst and collapse. The second is API RP 2RD, which states that the rod thickness requirement increases to maintain the static riser stress below the normal operating allowable load 2/3 yield strength. The second is the installation. Offshore installation rates are a major cost concern for deep water field development. Installation costs are a combination of vessel requirements, time, and mobilization. Vessel requirements based on depth and pipe weight and diameter. And every day the vessel is out there, it costs you money. The vessel, during a time of like a catastrophe, will either fight or flight, which will cost money. That means they'll either stay and tough it out, or they'll leave when something bad happens.
Hey guys, William Fernandez here, and I'm going to be talking about what progress we have made so far concerning the engineering standards that we have researched. So far we have attained API RP 1111 and 2RD and are reading through the practices. We have decided it would be most appropriate to do a comparison between the Barlow equation side by side with API RP 1111 and 2RD. After some extensive research in 2RD, we have realized that the different versions of 2RD contain a number of different valid methods to determine pipe failure, including references from API 1111. Therefore, we will use other methods described in 2RD along with 1111. One method in particular that we are set on doing is the von Mises stress analysis, which is required by the 1998 version of 2RD. Von Mises stress is a triaxial equivalent stress which represents the combined axial, tangential, and radial stresses on the pipe. This stress analysis along with API 1111 is much more accurate because it considers external hydrostatic pressure, minimum yield stress, and tensile stress on the pipe, where the Barlow equation only considers minimum yield stress of the pipe. For this reason, it may be why the Barlow equation is so conservative, because it is so simple and in reality there are so many parameters which can either make the pipe more susceptible to failure or even stronger. We also learned about design factors that risers must have in the design phase. We may plan to utilize these design factors and incorporate them into our calculations. We also now understand that risers must be hydro-tested before put into operation. A hydro test is a preliminary test done after installation to determine the integrity of the riser. High pressure water is pumped into the riser, which must be stabilized at 1.25 times the maximum allowable operating pressure, or MAOP. For our project to have any credibility, we must simulate this hydro test in our calculations because of current government regulations.
My name is Barakat Nagatu. I'm focusing on progress report on major issues of analysis and design criteria. Major issues of analysis. This is the issue that we have facing right now, and then we might not gonna see all of this one, but we have a probability of looking on high pressure, high temperature, and then strengths, and then risers configurations. So for the major issues of the designs, we have to look on the strengths, the hydrostatic collapse, and then buckling propagation, and then fracture. But at the same time, because of certain limitation, we might gonna see all of these parameters. So we have so many criteria, of course, in globally, but we have to only focus on API RP 2RD. So what is API RP 1111? API RP 1111 is American Petroleum Institute recommended practice, which has implementing and then controlling the design of a riser in USA. For instance, criteria have been applied to calculate required steel pipes wall thickness for breast strengths, collapse strengths for pipe in operation and in installations. Riser designs. So for riser design, we have to satisfy government codes, regulatory codes, standards such as ASME grading, recommended practices, and industrial standards. Design beyond codes, laboratory test, and finite element analysis. For the finite element analysis, after doing some researches, we have decided to attempt to do a finite element analysis comparison with API 1111 and then 2RD. However, as of now, we are not sure if we have the resources and the capability to perform such analysis. Here is Sarab to talk more about what we have researched for the finite element analysis.
My name is Sarab, and today I'll be talking about our progress on our finite element analysis. So, as part of our project, we want to model a floating riser. To model a floating riser is a difficult task because there are so many stresses and dynamic loads involved. Also, it's difficult to write a program for it because you end up with a lot of partial differential equations, and to solve those requires extensive numerical analysis and other advanced mathematical techniques. Instead, we found a software called LISA, which is freely available. LISA is a finite element analysis package with an integrated modeler, multi-threaded solver, and graphical post-process. This will meet our need for software. However, we need to learn to use the software, so we have taken steps to start that process. Each one of us has downloaded the software and experimented with it. Several tutorials have been watched to learn more about static analysis, pipe flow, and buckling. We have learned the basics such as modeling something in 3 dimensions and 2-dimensional, or changing the materials, creating our own grid coordinate system, and other basic tasks such as those. This is our current progress on finite element analysis. We found the proper software and we're starting to learn how to use the software properly.
Hi, my name is Thomas Conan, and I'll be talking about the quantitative risk assessment. A quantitative risk assessment is a process of assigning a numeric value to the probability of loss based on known risks and available objective data, according to InvestorWords. Many industries, especially oil and gas, have used this system to quantify risk. In our case, the most important risk is the loss of life. A QRA may be a requirement of legislation and/or internal company governments to show that risks are identified and controlled to an acceptable level. The criteria for risk acceptability may be defined by local regulations and/or company investment policy. Typically, a QRA can be defined as the formal and systematic approach of identifying potentially hazardous events, estimating the likelihood and consequences of those events, and expressing the results as risks to people, the environment, or the business. We will employ the traffic light system, which measures the impact and probability of a given set of values for our riser design. We'll measure the impact on a monetary scale based on how a certain design criteria will cost if failure occurs. In addition to cost impact, we will also study environmental impact. We can measure unexpected and expected events in a traffic light system. We'll also use the fault tree analysis, which quantifies events based on one particular event happening. Here's our references, and thanks for watching.